Wen-jie from Ant Research and Alibaba Group. It is a joint work with Zhicong, Qizhi, Yuchen, and Cheng. And today I will present our work on training a gradient boosting tree model using secure two-party computation technology. We present many optimization to achieve a better communication efficiency and a faster computation. And we first give a simple description of what is a decision tree is. Given this table with many columns of the attribute, and the final column is the label. Our target is to build a branching model, node fx, to give a prediction which we hope to close to the ground truth label, like do a yes or no this branching. And a gradient boosting tree consists multiple of these decision trees. We build those trees one by one in a boosting manner. That is, the nth tree is built using the gradient information from all the previous n-1 trees. And the prediction result is the sum of each of these trees output. And why gradient boosting tree is used in many companies? Because of the high accuracy. And the second is the most important thing is it can be, to convince the customer that why his label is predicted in that way. And okay, we come into a private gradient boosting tree using secure multi-party computation. And let's go a little bit deeper into the GBDT building. To build a tree, we first need to compute the gradient information, the first gradient and the second order gradients. And we have to split the tree node one by one. And to split a tree node, we have to come through all the possible split on all the attributes to find out the best split point to give the maximize this gain formula. And all the samples will separate according to the split. And all this computation should be done in a private way. And here is our goal. In our paper, we want to do is a vertical partition setting. That is, the attribute is distributed across two parties. For example, a bank holds some of the attribute, and the other, insurance company holds the other attributes. And the privacy requirements here is we assume semi-honest setting, and we will review the split point, like which attribute to use and which the threshold to the owner of that attribute only. Like Alice holds this attribute age, so he can finally see this threshold. But we want to hide the sample distribution, like which sample is partitioned into that node and other is not. This kind of information have to be kept secret in our approach. And there's many actually related methods using federated learning or just simply 2PC. But federated learning have to leak more information, like the sample distribution, or they just compute the gain in clear text. And the current 2PC method, little bit heavy in the computation and actually very heavy in the communication. So there's challenges. Actually, the real challenge is we have to minimize the communication as much as possible, because when we cooperate with a bank, they only can offer a very low bandwidth. Okay, here's our tools. In a very brief view of the 2PCs, all the messages in the middle is secret shared or just homomorphic encrypted. And we only decrypt the final result, just like the threshold and the attribute index. So we mix with the secret sharing and using average transfer as the building block and linear homomorphic encryption. Just we We only need to do addition, actually. And we will switch between two of them because homomorphic encryption cannot compute the nonlinear function very efficiently. So for that part, we use secret sharing. And for some part of the computation, we will switch to the homomorphic encryption and do the computation and then switch back. Okay, we will go through the pipeline of a Squirrel. We have three kinds of data, so we just make it different colors for the plain text, for the secret share, and for the homomorphic encryption, encrypted data. But the encrypted data is, is held exclusively. That the Bob holds the ciphertext that is encrypted by the Alice, so he cannot see the plain text. But he can also, but he can still do the computation. So from the plain text to the secret share, we will evoke some 2PC protocols, and we will also converge between the secret share and homomorphic encryption, obviously. And there are three one-stop steps of our approach. The first one is to run a private set intersection because we have doing the vertical setting. And then we do the data encoding, like barcoding locally. That we cannot actually iterate all the possible attributes, all the possible split. We just do some of them. And actually, the local data is actually a sparse matrix, like a binary matrix with very sparse. Actually. And we will the final step is to initialize randomly for the first prediction vector, like just set up or 0 or 1. No, never mind. There's it comes to some iterative steps. The first step is to compute the gradient using some kind of protocol for the sigmoid because for this talk we're just doing the binary classification. So we need to invoke some 2PC protocol for the sigmoid. And then we convert the shared gradient to a homomorphic encryption gradient to do the aggregation. Actually, like we aggregate according to the attribute. The reason why we use HE because it enables us to use some local computation instead of very expensive sorting in a 2PC manner. Because we are doing the vertical setting, actually. And finally, we will convert back to the secret share because we have to move to the next step to compute the maximum gain. And the step 3 to step 5 is actually just simply following the plain text gradient Boolean tree training. So we just skip more of them. And we will, the my index will be revealed to the corresponding holder so that the step 4 and step 5 can proceed. And finally, coming into our proposed optimization, actually the iterative steps are very similar to the previous. And for the existing method, they just use simple parallel or ISA-like encryption to encrypt each of its gradient. So then they can do the simple HE addition. However, it can be very computation bounded because each encryption takes 1 or 2 milliseconds, and we have 1 million or 2 million samples. So just the encryption part, it will take maybe 1 hour, and the communication also be quite large, because we have to repeat this process for all the tree, almost half of the tree nodes. So our proposal is to switch the homomorphic to a ring LW-based homomorphic encryption, and to encrypt the gradient vector as the coefficient of the ILW polynomials. And ILW is a homomorphic system which can handle a polynomial as a whole. So each of these gradient vector will be placed on each coefficient of the ILW polynomial. And it can be very faster than using the previous one because we encrypt 4,000 just one time. And the communication also be much more less than just using simple maybe pair encryption. And one problem is that we have to do the aggregation, so we have to pick up a specific encrypted coefficient to do the add. So actually, luckily, we can do it very cheap because we are using the 2-power ring. So from RLW to LW actually is very cheap. And the LW addition can be accelerated using AVX, very simple. And like we can do it for 61K LW addition per second per CPU core. And we also propose a method to compress the result because the encrypted table may consist of hundreds of LW ciphertexts. We just to compress all of them to further reduce the communication efficiency. For the detail, just refer to the paper. And the second optimization is some kind of interesting sigmoid protocol. And for the previous one, they just use numerically approximation or just compute a very expensive exponential function. But given the large number of the sample, so doing such methods cannot be very practical within a very low bandwidth actually. So our proposal is to use 3-segment approximation with the margin is just a linear because the sigmoid is linear on the margin. And for the middle branch, we use some kind of Fourier series. It may seem very hard to compute, but we find that actually for the secret sharing, it has a very nice property to compute even within a single round. And if we write down the scale sign function, for the first line, it's just a definition of arithmetic share. And for the second line, it will be absorbed by the periodic property of the sign function. And for the last line, it's just double angle of the sign function. And the nice part is that actually Alice and Bob can compute locally for these 2 parts. And finally, we just need doing some modification to get the sign function. So it's just one round protocol for the middle branch. And I'll come into the experiment. I run out of time. Actually, we can do build 1 trees within 3 minutes using under the 1 million samples and 20 features within a very low bandwidth, I think. And let's zoom in a little bit. The computation time and is scaled linearly with the sample size and the feature size, because we have to do a full scan for each of the 3 nodes because we keep the sample distribution secret. But the communication scale more gently with the number of features. We maximize we scale the features from 10 attributes from 10 to 100. The total communication just maybe double. And we show pretty improvement over the existing method, even under their sweet spot setting. Like the period need a very fast bit bandwidth, and the second one they use trusted hardware to generate the multiplication triple. Even though our method can improve them. And conclusion. We propose to use ring LW and LW conversion to do the fast gradient aggregation, and we also propose a method to compress multiple LW ciphertexts to one RLW ciphertext for less communication for the aggregated table, and we show some pretty interesting and cheaper sigmoid function. Very surprisingly, we even compare with the function secret sharing based FS-based sigmoid. Our communication is just slightly larger than them, but with much more faster. And we come up some follow-up operation optimization. So just check our ePrint version. Thanks.